Hey, good morning, everybody. We ready? It's felt like a Monday today for me. All right, anybody remember what we were doing last class? Cal 3? Yeah, so what we were doing was we were saying, okay, we have these new functions of two variables, right, that make these surfaces. And we said, all right, well, if we've got that, then we should be able to talk about the limits of those functions. And we were seeing that it's very hard to show that a limit exists for a function because you have to check every path. And we did some examples where we were able to show that the limit did not exist by showing from different paths we got different answers. And I told you that generally it's really hard to do to find the limit of a function of two variables, but we do have this thing called the squeeze theorem, which sometimes can help us. It depends on the problem. I mean, I could give you a problem you can't do with the squeeze theorem, but sometimes things look just right, we can use this theorem. So the theorem is right here, and it's really ugly when you look at it, okay? So I think it's better if we try and visualize it. And to visualize it, what I'm going to do is have you consider the squeeze theorem from Cal 1 first. So in Cal 1, what we said is, if we're trying to find the limit as x approaches a of some function, right? And we're trying to figure out what it is. But we are able to say this. So if that function f of x always lives between two other functions. Okay, so f of x is always between two other functions. So if this is g and this is h, if I know that f lives between those, right? That the y value of this function is always less than this y value, always greater than that y value, then it's always between these two, right? And if that's true, and we have that the limit as x approaches a of the h function is equal to the limit as x approaches a of the g function. In other words, if these two functions h and g go to the same place as you approach a, here's a, let's say h approaches something here, and g also approaches the same value. So this right here would be whatever that limit is. So if h and g both approach, as you approach a, and it would be from both sides, if they both approach the same limit value equals L, okay, then what can you say about f? That this limit must be what? Well, as we approach a, this limit should also be L, right? Because the f function is squeezed between. So if f has to be between these two, it's going to go to the same place that those two go to, right? So there's two things you have to have for this squeeze theorem to work. You have to have that f is bounded by two functions, a function below it and a function above it. And then you have to have that both those functions, the lower and upper bounds, both have to approach the same limit as you approach some point. Then you can be guaranteed that the f function must also go to that same place. What would that look like with surfaces? You have a surface on top. That would be like your g. Then you would have a surface on the bottom, which would be your h. If your f is always between those two sheets, and the top and bottom sheets go to the same place, right? As we approach some point in the domain, if those sheets come together, then the sheet in the middle should also go together as well, right? That's the idea. So that's what this theorem, that's what this little theorem says here. This is it written out like algebraically. It says, all right, so let's say that the function you're looking at is bigger than this one. So this is the sheet that's below it, and that's the sheet that's above it. And we have that. Well, we just get right to the inequality. Whatever the limit is, whatever the limit of this one is, must be less than the limit of this one, which is less than the limit of this one. So if these two go to the same place, then the one in the middle must also go to the same place. So I'm going to just get right to a problem so we can see this. Here it is. Your next take-home mini-exam 3 is due a week from today, right? Okay. Please reach out if you have any questions, all right? I may have mentioned this before, but my willingness and excitement to help you is inversely proportional to the amount of time, no, directly proportional? Sorry, directly proportional to the amount of time left before it's due. So if you contact me a week before, I'm like, hey, I'm here to help. If you contact me an hour before it's due, I'm less likely to want to help, all right? So the sooner the better. I hear from you, yes? Here we go. We're approaching 0, 0. So let's just check. What happens if you replace x and y with 0? On top you get 0, on the bottom you get 0. 0 over 0 is undefined, so you know, this thing is not defined at 0, 0, but we're trying to figure out what happens as you get closer and closer. And then we could start trying all these different paths, right? And I'm not going to go through it, but if you try a bunch of paths, you're going to get the same answer. I mean, same thing every time, right? But we said you have to check every path. That's impossible. So instead what I'm going to do is I'm going to see if I can't somehow look at this f of x, y, this function. I'm going to try and look at it and squeeze it between, oops, that's a squared, and see if I can't squeeze it between two things. So the question is, this is like my lower one, h of x, y. What would that be? And then over here, g of x, y. What would that be that I can squeeze this between? So let's start with the one on the left. And I'm just kind of like guessing here. I don't know what's going to happen. But I know for sure that every term in here is positive, right? Because I got a bunch of squareds. So I know for sure that this ratio has to be greater than or equal to 0. And you could say that that's a function, right? It's just a flat, it's just the xy plane, right? So that technically is a function that is below it. It's just a flat sheet, the xy plane. And now I need an upper function that is always bigger than this. And then I'm hoping that when I take the limits on the outside functions and let xy go to 0, 0, that both sides will go to the same place. Well, this can only go to one place, what? 0, right? So I'm hoping whatever I put here, when I take the limit, it's going to go to 0 as well, right? But wait, didn't I just say that we can't do limits? Like, to do a limit, you have to check every path. So if I put something over here and do limit, I'm going to run into the same problem of checking every path. Right? Unless what I put here is a function of a single variable. Because if it's a function of one variable, then you're back in Cal 1, and then you only have to check from both sides, not every path leading to it. Does that make sense? If it's only one variable in there. So, should I just put it first? Let me just put it here first, and then we'll see how I got this. Now, you have to be asking yourself right now whether or not you believe that's true. Do you believe that this is always bigger than or equal to this?
Yeah.
Yeah? Do you have a justification for that?
So as y gets larger,
Uh-huh.
the middle function that we have gets smaller because it's squared. Whereas when we look at the right function, y is going to continue to...
I see what you're saying. This is going to oscillate.
Yeah.
This one's headed to 0. But I agree with you, but what about x? See, because this has to hold for x as well. So x might be actually making that have an impact on that as well, right? It's good to think about that. I mean, it's... Continue. Anything else? I mean, it is true, okay, but I need us all to see why that's true. Let me help a little bit.
Oh, yeah.
That's the middle, right? That's the middle.
Can we cancel x squareds?
Can't cancel the x squareds.
Oh,
Algebraically, right? Because we could do it.
yeah,
Yeah.
I can see now.
Yeah.
Multiplication x squared.
But that's the same thing, right? This right here is this, right? Okay. And this is this. So somehow I'm saying that this has to be smaller than the coefficient that's in front of this. What is the coefficient in front of this? 1. Can you convince yourself that that's less than 1?
Is it because sine squared is always between 0 and 1, and the bottom is always going to be greater than 1, basically, right?
What's always greater than 1? I'm not sure what.
Denominator. Like
This right here.
Yeah.
Well, the denominator is
Unless
always
it's
going to be greater
zero.
than the
Unless it's zero,
numerator because you're taking the numerator and adding to it.
Okay, yeah, so look, what I'm trying to get everyone to see is that this has to be less than this, right? I'm trying to convince you of that. So if I peel that off, right? I'm trying to show you this, right? This is the question, is this true? 1 times sine squared y. So if I'm trying to convince you if that's true, these two are exactly the same thing, right? So you can ignore this. Really what I'm trying to show you is that 1 is bigger than that, which means you have to convince yourself that this is smaller than 1. But it has to be, because this and this are the same thing, right? So if that wasn't there, that would be 1, right? If I add something to it, this is always positive, right? Well, it could be 0, couldn't it? But, you know, that would be like the extreme case. If that's 0, right, imagine that's 0, then aren't these equal?
Yeah.
Okay, so if it's anything other than 0 here, this squared, that's a positive number, this number is bigger than that number. And so it's less than 1, isn't it? So this is true. And if that's true, then what I can do is from here I can say, all right, well, by the squeeze theorem, if I take the limit as xy goes to 0, 0 of 0, that's that function, that must be less than or equal to the limit as xy goes to 0, 0 of this thing. But that must be less than or equal to the limit as what? I only have one variable here, right? There's only one variable here. So this is just a cal 1 limit. Limit y goes to 0 of sine squared y. And what's sine of 0? 0. So the way to use the squeeze theorem is that you have to get these two functions on the side. You need to get them to go to the same place. And the only way to know that this one would go to the same place every time is if you can get it down to one variable. And then you can do it. So that goes to 0, right? That goes to 0 because the limit of a constant is a constant. So if those two limits on the outside have to go to 0, then the one in the middle does too. So that's it. We're done. So therefore, what is that limit? It is 0. See, you don't have to check every path. I think there's one or two of these in the homework. See how they go. All right? See how they go. They're tricky. All right, continuity. So limits in Cal 1, we do limits, and then we do continuity. So let me remind you again, in Cal 1, what continuity was. There's a definition for it. But in Cal 1, we had this. At x equals a. So this is from Cal 1, right? So continuity, x equals a. Here's the definition. It says the limit as x approaches a of your function must be equal to f of a. So visually, here's what it meant. If you want to talk about continuity of a function at a point A, then what we need is this. We need the function from the left and from the right to be approaching the same value, okay? That means the limit exists, right? So that's this left side. This limit exists, okay? And what does that limit have to be equal to? The value of the function at that point A. So where the function is headed is actually equal to the function's value at A, And so you have continuity at that point because from both sides you're headed to the same place and it's a solid dot there. If you take this out, you lose continuity. If you move that point up here, you lose continuity, right? So to have continuity, you have to have the limit exist and that. So with a surface, it's the same exact idea, and that is, in order to have continuity, you have to have your limit going in from any direction going to the same point, and then once you get to that point, it has to be filled in with a solid dot. So it's the same exact definition, just dealing with sheets instead of a curve. So here's the definition. And we're not going to do any examples of this. This is just so we have the definition, that's all. So we're saying here to be continuous at a point in our domain. Remember, our domain is on the ground. To be continuous at a point in our domain, as we approach that point on the function, so as you move in from any direction, you must be equal to the value of the function at that point. So that point must be filled in. Okay, now, for us, we're just going to talk about what functions are continuous and what aren't. That way we don't have to worry about checking for continuity. So in this class, for functions of several variables, all polynomial functions f of x, y are continuous on R2. Do y'all know what a polynomial function of two variables would look like? Y'all know what a polynomial looks like in college algebra, right? Like x cubed plus 4x minus 1. You just basically have x's to powers. Those powers have to be, what, non-negative integers? So you could have like x to the 0, x to the 1, x squared, x cubed. Those are polynomials. A polynomial function with multiple variables means not only do you have x's to powers, but you also have y's to powers. So that's a polynomial function with several variables. Rational functions are the same thing. You have a ratio of two polynomial functions is a rational function. And then, so both of these are continuous. This one is continuous everywhere. Polynomials are continuous everywhere. Rational functions are continuous on their implied domain. So as long as the denominator is not 0, you're continuous. And then composition of two continuous functions is also continuous on their implied domains. Again, this is not going to be a big deal for us. This is just for us to know what type of functions are continuous. That's it. And we get to homework and we're done. This section right here is not a major section in terms of, like, if you don't understand this, like, it's not the end of the road, all right? Like, if you struggle with this. Things like knowing that the cross product of two vectors gives you a vector that's orthogonal to both vectors, that's the type of thing that you need as we continue to move on, right? Now, the next section is very important. We are going to talk about partial derivatives now. I can remember as a Calculus 3 student learning about partial derivatives for the first time, and my professor standing up there on that board in that auditorium trying to draw it and me not understanding at all what he was talking about. So this is, I think, going to be pretty easy for us to understand because we have computers and we can visualize it, right? So let's go back to Cal 1. We're about to talk about partial derivatives. Let's go to Cal 1 and let's just remember what a derivative is. I know you all know what it is, but let's just go through the actual buildup of this. You're given a function, right? And then the derivative of that function at some point is the slope of the tangent line at that point, right? So as you move along that curve, give me some x value, and I will give you the slope, and it'll be different for every input, every different x you give me, right? Will give me a different slope. That's Cal 1, derivative. We're going to do the same thing now, but on a surface. And we talked about this last time, that when you're on a surface, it's going to be a little harder because we can't really define a line. And we said, what, that we'd probably be talking about what instead of a line? A plane, right? So let's see if we can't visualize that better. So here is a surface. Would y'all mind killing one of those lights? Let's see. Try the gray button top right. Try that. Or right side. Yeah, try that. Yeah, that actually makes sense that that's on that side. It's not like that in all the rooms here. All right, y'all see the surface? See this surface? Okay, y'all see that point? The black point right there? Okay, I'd like for us to talk about the slope of the tangent line there, which, again, doesn't make a whole lot of sense because, like, there's an infinite number of lines that would go through that you could argue are tangent to that curve, right? So let's do this. Let's cut this surface. So here's the surface sitting out here, right? Here's the x-axis, here's the y-axis. What I'm going to do is I'm going to pick a y value. Okay, let's say y equals 2. And I'm going to slice through the surface just like this with a plane. Okay, the plane y equals 2. So I'm holding y equals 2. I'm holding y to be a constant. If I let y equal 2, then I'm slicing it like that, right? Slicing that surface with a plane. And you can see that when I do that, the green plane intersects that surface. I'm going to pull the surface out of here, and where the green plane intersects that surface, I now have a curve that looks more like a Cal 1 problem, doesn't it? And if I rotate it, let's say if I rotate it just perfectly this way, maybe, something is wrong with the code, because I used to be able to just hit this button. It would give me that view from infinity, and it's not working. I don't know why. So there it is. There it's the slice. So the best I'm going to be able to do is something like this. And I'll pull that. Man, this thing shakes so much, right? Okay, if I take that out, now we're back in Cal 1, aren't we? If we hold the y to be a constant, we're back in Cal 1, and I can easily define the slope of the tangent line there, right? And I can even, make this a little smaller. I can even move my x, right? Move my x along that curve, and my slope of my tangent line will change, won't it? Right? Remember, that's with me holding y to be constant. What if I change the value of y? I said y equals 2, right? What if I change it to y equals 3? Is it going to change that curve? Absolutely, right? That curve will change. So let me bring the surface back in. Okay, and let me kind of rotate it back this way. And yeah, let me go back to normal. This is so messed up. Okay, I'm going to change the y value. So I'm still holding y constant, but let me just move it real quick. See if I move it over here? Whoa. Yeah, that's definitely a different curve, isn't it? This is really annoying. That's definitely a different curve, right? So if you hold y value, with the y value constant, you will have a curve. You change the y value, you have a different curve. But again, it takes us back to Cal 1, and we should be able to do a derivative that way. Okay, that was me holding the y value constant. Could I have held the x value constant? Could I have instead of the y? What the hell? I'm going to throw up. I'm getting like nauseous up here. I could have, right? Wow, this thing is not wanting to rotate for me. Move that x value back. Okay, let me go back up there. So if I hold the x value constant instead, then what I'm going to be doing is I'm going to be slicing through that with a plane that is perpendicular to the green one, right? It's orthogonal to it. And so we should get a different curve, right? And I take that green one out. Take that green one out. Let's pull that surface back. And there's, if I'm holding x constant, I have a different curve. And then I have, of course, a slope of a tangent line. Maybe. Oh, wrong one. Right? I have a slope of a tangent line. And as I change my y value and move along that curve, I get different slopes. So this is what a partial derivative is. You're taking a derivative, but by holding one of the variables constant, we call it a partial derivative. All right? There is something called a total derivative, but we'll talk about that later. Right now, we're just going to look at this idea of a partial derivative. Okay, is there anything that says, right, we had this surface, is there anything that says I had to use a plane that went this way or this way? Could I have cut with a plane that went like some other way, right? Could I have? Sure, that's coming later. It's called the directional derivative, right? But for now, we're just looking at these two, which seem very natural, right? Cut it with the plane that's, hold y constant, hold x constant. It seems natural to just do that. Yes?
Could you use like a z, do it on the z plane?
You could, but then you're going to run into problems because when you cut it, that curve you get may not be a function, right? It could.
Yeah.
So we won't have that. If you're doing a function of x and y, then your planes, you're going to want them to be vertical like this. You can turn them, right? So you could have them like y is constant, x is constant, or anything in between, but you wouldn't want to start to tilt it because then you'd have issues. All right. So that is the idea of a partial derivative, that picture, right? So given some function f of x, y, if we hold the y constant, then we call the derivative the partial derivative with respect to x. It's a little bit backwards. If you hold y constant, it's called the partial derivative with respect to x. I guess you could look at it like with respect to x means the x is your variable, right? That's the thing that's still changing. And this is the notation we use for it. No more primes, okay? You know how we used the prime mark in Cal 1? Just a prime for the derivative? We're not going to use the prime mark anymore. We're going to write f subscripted with an x and then xy. So this is like, it's kind of like this notation we had in Cal 1, right? We all knew that that meant the derivative, right? We can no longer be that ambiguous with our notation because we need to know what is the variable and what we're holding constant. So in order for us to do that, we have to somehow represent what variable is still a variable. So we put an x here, and of course, well, it's not a function of a single variable, it's a function of two variables. All right? That is called the partial of f with respect to x. We are holding what constant here? Y. All right. Now, the other way around, the notation changes, right? So if we hold the x constant, then we call it the partial derivative with respect to y, and we write it this way. Yes?
Is there a Leibniz notation for that?
There is Leibniz notation as well. Yes. Which I'm going to get to the different notations here in a minute. Okay, see the difference, right? Here we're holding x constant. Y is our variable. So let's just make sure that we can do this mechanically before we move on. Make sure we understand the mechanics of how to actually do a partial derivative. So you all see that function up there? Let's start with part A. Let's find the partial of f with respect to x of xy first. I want to know what happens when you plug in 2, 1. But before I get to that, let's just take the derivative first. So when I do this, what am I holding as a constant? Y, right? So let's start looking at this and take the derivative of this function. Now this is an example of a polynomial function of two variables. So let's just go. I have a bunch of additions, right? So I can do them one by one. What's the derivative of y cubed?
3y squared.
3y squared if y was a variable, right? Is y a variable here? No, y is a constant, right? So imagine just plugging a number into this. 2 cubed, it would be 8. What would the derivative of that be? 0, right? So because y is a constant, that's a constant, and the derivative of that is 0. Plus. Okay, what's the derivative of 2x? Now, x is our variable. So we go back to like Cal 1 idea. What's the derivative of 2x? 2. Okay, plus. Okay, be careful with this. X squared y to the fifth. Y to the fifth is what? A constant. So what happens when you have a constant attached to a function like this when you take a derivative? What happens to that constant? It comes along, right? So I'm kind of going to ignore the y to the fifth and take the derivative of x squared, which is 2x. So you could write 2x times y to the fifth. See, the y to the fifth is a constant. I'm just bringing it with me, right? And just focusing my attention on the derivative of the x squared. And then finally, derivative of 10. Well, that is a constant. There's no, always. So the answer is just 2 plus, 2x y to the fifth. What the hell does that represent? What does this mean? It means for this surface, right? For this surface, for this surface. If I hold y constant, slice it, right, at some value of y, I'm going to get a curve. And the slope of the tangent line on that curve is equal to this. So what do you need to figure out the slope of that tangent line? You need what two things? The x and y. So remember, we slice through here, we have a curve, right? I need to know the x value and the y that you're holding constant, and then I can go up to the curve and give you the slope of tangent line. See? So now that's what this is saying. What's the partial of f with respect to x at 2, 1? Well, all we do is replace x with 2 and y with 1. Oops, x with 2, y with 1. So we get 4, 6, 6. I'm really wondering if y'all see this or not. Do y'all see the surface I'm talking about here?
Well,
It's here, right?
space.
I mean, like, okay, so the answer was 6, right? So what this is saying to us is this. Some surface. Where are we slicing it? If we're talking about this right here, where are we slicing it? Y equals 1. So I'm slicing it at y equals 1. This is y. Slicing it right there, and I have a curve, right? Right here. And when I go to x is what? 2. Y is 1. And go up to this curve. The slope is what? 6. Okay, which way is it 6? 6 relative to me or to you? Because that's 6 to me, but that's negative 6 to you. So which way do you think we're looking? From my point of view or yours? Look at your axes, right? What's the positive direction of x is this way? So this curve, we said we were back in Cal 1, right? But we can look at it from that side or this side. We're actually on your side because the x-axis is positive here and negative here, right? Like to you, you're seeing that curve like it was a Cal 1. I walked around to the other side of the board. That's where I'm looking at. So it should be 6 like that, okay, to you. All right. It's not going to matter later because we're going to use that along with a different one, and then from that we're going to be able to create a plane, and that's really what we're interested in. Okay. Here's another way to look at it. Here's another way to look at it, just so we understand like kind of multiple perspectives. What we're saying is if this surface is here, right, and we went to 2, 1, right, 2, 1, and we went up to, we were a point right there. What we're saying is if I'm standing on the surface, imagine me standing on the surface at that point 2, 1, right, and I start facing out the positive direction of the x-axis, right, we're holding my y1, and I take a step forward. What's going to happen? I'm going to go up, right? By what rate? What's my instantaneous rate of change there? 6, right? Now, if I turn around and go this way, right, what's going to happen? I'm going to be going down, right? So this is really, you can think about things like on surfaces and like if you point in certain directions, which are you going to be doing this or that, right? Okay, what about the next one? Next, part B.